Hello there, and welcome to the Dreamy Scientist. If this is your first time here, I want to say a warm welcome. This channel is all about calm, peaceful journeys into the amazing world of science. These soft and relaxing stories are meant to help you fall asleep with a mind full of new and curious thoughts. And if you've been here before, welcome back, Dreamy Explorer. It's really nice to have you here again. Tonight, we're not staying on Earth. Instead, we're going to gently rise above it. We'll drift slowly into outer space, a place where the idea of up and down no longer makes sense. In space, the ground isn't really needed. There's no floor to stand on. We're heading out there not for loud rockets or the busy sounds of launch control, but to explore something much quieter and much more mysterious: gravity. Gravity is what keeps your feet on the ground. It's the reason your cup of tea doesn't float into the air. It's why stars and galaxies hold their shape. It's even the reason your toast always seems to land with the jam side down. But what if we could step away from gravity just a little? What would it feel like to be in a place where gravity isn't always pulling on your arms and legs? In this video, we'll learn what it really means to float in space. We'll look at what happens to astronauts when they orbit Earth, how gravity affects our bodies and our thoughts, and how Einstein completely changed the way we understand this invisible force. And don't worry, it's all going to be light, gentle, and sleepy. Perfect for relaxing. I should probably let you know, this video might be a little too interesting. I'll try not to make it too exciting, but if you find yourself staying awake and thinking deeply about how space and time bend and twist, well, at least you'll be learning something. That seems like a good trade for a few minutes of lost sleep. Before we float away, I want to ask you for a small favor. If you enjoy this quiet adventure through space, please consider giving the video a like. Maybe even subscribe to the Sleepy Scientist. It really helps more curious dreamers find their way here. And if you feel like chatting, let me know in the comments, where are you watching from in the world, and what time is it right now? There's something special about imagining people all across the globe, from Sydney to Stockholm, from midnight to morning, getting cozy with a warm drink, lying down under a blanket, and sharing in this peaceful curiosity. We're all different, but in this quiet moment, we're connected by the same wonder and love for gentle science stories. Wherever you are, I hope you're nice and comfortable. Maybe you've dimmed the lights, fluffed up your pillow, or turned on a star projector. Maybe your cat has already curled up and started snoring. However you're listening, I invite you to let your body relax, your breathing slow down, and your mind FT freely. There's no rush. We're not in a hurry. We're just floating gently. Because in space, there's no such thing as up or down, only quiet, graceful motion. Astronauts say that being in microgravity feels both freeing and confusing. You can float, spin, or glide with just a little push. It's playful and strange at the same time. But here's something curious. Everything in space is still under gravity's control. It just doesn't feel that way. That's the mystery we're going to explore. Weightlessness isn't what it seems. It's not that gravity has vanished. It's actually something trickier, a constant falling motion, a kind of smooth, never-ending movement through space. To understand this strange experience, we'll visit not only the International Space Station but also the brilliant minds of Newton and Einstein. We'll look at black holes, orbiting planets, and even how our own bodies change without gravity. But don't worry, we're not blasting off like a rocket. This will be slow, soft, and easy, like a gentle float upward. A quiet trip into the invisible threads that tie the universe together. So before we go, take one last moment to notice the ground beneath you. Whether you're lying in bed or sitting on the couch, feel how gravity holds you close, like a soft hand resting on your back. Gravity has been with you your whole life, since the moment you were born. But for a little while tonight, we're going to imagine what it's like to gently let go of that pull. To float beyond it. To explore what secrets gravity has been keeping from us, hidden in plain sight. Because sometimes, the best way to understand something is to step away from it for a while. Alright, sleepy scientists. Let's begin this peaceful adventure, floating in space, and learning what it teaches us about gravity. So, what exactly is gravity? It sounds like a simple question, but once you try to explain it, you realize it's not so easy. You might say, gravity pulls things down. And yes, that's true. But that's like saying sleep is what happens when you close your eyes, true, but not the whole story. Let's go back in time, not all the way to the Big Bang, just a few centuries, to the famous moment when an apple supposedly fell on Sir Isaac Newton's head. Spoiler alert, most historians agree it probably didn't hit him. But it did make him think. In the late 1600s, Newton came up with a big idea. He said gravity is a force, an invisible pull that all things with mass give off. That means everything that has weight, like you, me, the moon, or even your dog, pulls on everything else. But we don't feel it because most of us are too small to notice. The Earth, being huge and heavy, pulls with a lot more strength. That's why when you trip, you fall down instead of sideways. Newton explained that the more mass something has, the stronger its pull. Also, the closer you are to something, the more you feel that pull. That's why the sun keeps the planets moving in circles. It's huge, and eerie close enough for it to affect us. Not too close, though, just a safe 93 million miles away. Newton's idea was amazing. His rules helped us understand why apples fall, how planets move, and even how to shoot cannonballs farther. His theory worked so well that we used it for over 200 years. But then Einstein came along, a scientist with wild hair and even wilder ideas. In 1915, Albert Einstein introduced something called the theory of general relativity. It was a strange but beautiful idea. He said gravity isn't just a force. It's actually the bending and curving of space and time. Imagine the universe as a big stretchy sheet. If you place something heavy on it, like the sun, it makes a dip. Now if you roll a marble nearby, like Earth, the marble will move in a curve, not because it's being pulled, but because it's following the shape of the sheet. So gravity, Einstein said, isn't something the sun does to Earth. It's just the way Earth moves through the bent space around the sun. Planets aren't being pulled. They're simply sliding along the straightest path possible in a wobbly universe. Now, this is the part where your pillow might start to feel extra soft, and your eyes a little heavier, and that's okay. Let your mind float, even if the space around you isn't actually stretching. Newton said gravity was a force. Einstein said it was a twist in space. And guess what? Both were right, just in different ways. Newton's rules are perfect for everyday stuff. Cars, rockets, falling toast. But when things get really weird, like black holes, light bending around stars, or time slowing down, Einstein's ideas take over. Yes, you heard that right. Gravity even affects time. In stronger gravity, time moves slower. Scientists have measured this. Your head experiences time just a tiny bit faster than your feet do. Not enough to turn you into a time traveler, but enough to keep GPS satellites accurate, and to make physicists smile. If all this sounds like science fiction, don't worry. It's real. Gravity shapes space, time, light, and how we move. Astronauts don't float because gravity disappears. Even 400 kilometers above Earth, gravity is still strong, about 90% as strong as on the ground. They float because they're in a constant state of falling around Earth instead of into it. It's like being stuck in a roller coaster loop that never ends. But gravity isn't only about falling. It's about balance and order. Without it, stars wouldn't light up. Planets wouldn't spin. You wouldn't stay in your seat. Even your bones and muscles are shaped by gravity. It's part of you. We're so used to gravity that we don't think about it until it disappears. Then, everything changes. Your spine stretches. Your sense of balance gets confused. Your body fluids float strangely. And your brain, poor thing, tries to understand a world where down doesn't exist. We'll explore all that soon. But for now, just let this soft idea sink in. Gravity is more than a pull. It's the quiet rhythm of the universe. It decides how things move, where they go, and how they spin. It shapes seasons, oceans, and galaxies. And yet, it never makes a sound. It's the quietest power in the cosmos. So next time you feel your body sinking into your mattress, remember, gravity is holding you close. Not with a push or a shout, but with a quiet, gentle strength that's always there. And if you're still awake, don't worry. There's more peaceful wonder ahead. In the next part, we'll leave these big ideas behind for a while and float into the world of astronauts, where flying feels like magic, but gravity is never too far behind. Let's keep drifting. The rocket reaches the edge of space. At the very top, the car-shaped capsule separates. But instead of falling straight back down, it moves forward, very fast. Around 28,000 kilometers per hour. It's going so fast that even as it falls, the Earth curves away beneath it. You keep falling and falling, but you never hit the ground. You're not floating in place. You're actually orbiting. That's what astronauts do. They're falling sideways so quickly that they keep missing the Earth completely. Ever since the rocket dropped them into orbit, they've been falling, just in a special way. So when people say, zero gravity, that's not exactly right. The better term is microgravity. Gravity is still there. But astronauts feel weightless because everything around them is falling too. Here's a way to picture it. Imagine you're in an elevator. A very unlucky elevator. The cable snaps, and it starts to fall. For a few scary seconds, everything inside seems to float. Your apple, your tea, even you. You're not free from gravity. You're just falling at the same speed as everything else, so nothing pushes back against your body. That's what happens on the International Space Station. But without the fear, and with much better snacks. Astronauts live and work like this for months. It looks like fun. Flipping through the air, chasing floating M&Ms, but there are strange side effects. First, your inner ear gets confused. It uses gravity to tell which way is up. Without that signal, your brain says, "This must be a dream." Many astronauts feel sick at first. They also bump into walls, often. In microgravity, Newton's laws become very real. Every action has an equal and opposite reaction. Push off a wall, and you'll fly across the module. You might even crash into someone else's lunch. Even simple things become tricky. Try brushing your teeth, but the toothpaste won't stay still. Or using the bathroom when nothing wants to stay where it should. Astronauts must relearn how to move, eat, and sleep, as if they'd never lived on Earth. Sleeping is different too. No pillows. No beds. You float inside a sleeping bag that's tied to the wall. No tossing or turning. Just drifting inside a quiet cocoon. Some astronauts say it's the best sleep ever. Others, not so much. In microgravity, your body changes. Without gravity pulling fluids shift. Faces puff up. Legs shrink a little. Sinuses feel stuffy. They call it space face. It's not as cool as it sounds. Your bones lose strength. Muscles get weaker. On Earth, gravity keeps our bodies strong by constantly pulling down. In space, that pressure is gone, so the body stops trying. That's why astronauts must exercise 2 hours a day, just to keep from wasting away. Even your spine stretches. Some astronauts grow 2 inches taller in space. But don't get too excited. You shrink back down when you return to Earth. Still, it's a nice bonus, unless you barely fit in your seat already. But the most interesting thing about microgravity isn't how it changes your body. It's what it teaches us. Gravity shapes everything we do. We take it for granted. Objects fall, water pours, chairs stay on the ground. In space, all of that changes. The rules are new. Water forms floating blobs that stick to surfaces like jellyfish. Food must be sealed, sticky, or squishy. Otherwise, it becomes a choking hazard. You don't walk. You pull yourself along with your hands. There's no down. There's only where your feet are attached. At first, it's strange, physically and mentally. But slowly, the brain adapts. New habits form. Microgravity becomes normal. And then, astronauts return home. That's when everything gets weird again. Some forget they can't let go of things. They drop tools, trip, or expect pens to float. One cosmonaut said he almost rolled out of bed trying to turn over. So when we say space is weightless, we really mean your body feels weightless. Gravity never left. It's still pulling, it just doesn't feel the way you expect. And in that strange, soft confusion is a kind of beauty. Because gravity isn't just something that holds us down. It's something we've built our entire lives around, our bodies, our tools, our habits. Take it away, and even for a short time, the world becomes dreamlike. Quiet. Floating. Full of new rules. A place where flying doesn't need wings. And still, gravity follows, silent and steady. In the next part, we'll explore daily life aboard the International Space Station. How do astronauts eat, stay clean, work, and live in a place where everything, including the crumbs, tries to float away? We've left gravity's grip behind. We've learned that floating doesn't mean no gravity. And now we've arrived at one of the strangest places humans have ever lived, the International Space Station. It's a lab. A spacecraft. And for 6 people at a time, it's a home. A floating home that circles Earth every 90 minutes. From the outside, the ISS looks like a high-tech tin can with solar panel wings. But inside, it's a graceful dance of floating humans, blinking machines, and gently humming air. It's not fancy, but it's quietly amazing. So how do you live in space without everything turning into chaos? Let's begin with eating. On Earth, eating is easy. Gravity keeps food on your plate and drinks in your cup. In space, that doesn't happen. Liquids float. Food crumbles. Even a tiny tortilla bit can become dangerous if it floats into a fan. That's why space food is different. Meals come in sealed bags. Drinks are sipped through special straws with clamps. Spoons are magnetic or velcroed or tied down. Because losing a spoon mid-meal is very easy in microgravity. Fun fact, astronauts prefer tortillas over bread. Why? No crumbs. Crumbs float. And floating crumbs can end up in your nose, your eyes, or even worse, inside an electrical system. In space, a cornflake is a serious problem. Now, think about sleeping. You can't lie down, because there's no down. Astronauts sleep in small booth-like cabins. They zip themselves into sleeping bags tied to a wall, or ceiling, or wherever feels comfy. No pressure on your back. No weight on your joints. Just floating in silence. Many astronauts say it feels like being hugged by a cloud. No tossing. No turning. Just stillness. Though sometimes someone forgets to zip up and drifts away like a balloon until they bump into something. Sleepwalking's hard when there's no floor. Next up, hygiene. No showers. No baths. Water doesn't fall, so you can't stand under it. Instead, astronauts use wipes and no-rinse shampoo. They squeeze out blobs of water, catch them, and rub them over their skin. The water clings like jelly. And the toilets? They're masterpieces. Gravity doesn't help, so they use air suction. A vacuum system pulls waste away. Astronauts must aim carefully, using foot straps, thigh harnesses, and lots of training. Yes, there's a toilet manual. Yes, they practice. Yes, it's awkward. And yes, urine is cleaned and turned into drinking water. Yesterday's pee is tomorrow's Gatorade. NASA jokes. It sounds gross, but it's smart. Water is heavy to launch. Every drop is precious. What about moving around? You don't walk. You float. To move, astronauts push off with their hands and glide through the space station. At least, that's the goal. In real life, it's more like slow-motion bumper cars. You miss the rail, spin around, and try not to crash into anyone. To stay still, they use foot loops and handrails. And Velcro. So much Velcro. Everything is labeled and stuck down. Clipboards float. Pens float. Laptops float. You don't place things, You secure them. When you let go of something, you have to tie it down or it floats away like a stubborn balloon. Now, let's talk about daily life. Astronauts work around 12 hours a day, 6 days a week. Their time is planned down to the last minute. They do science experiments, fix things, do maintenance, talk with ground control, and exercise. That part is super important. In space, without gravity, bones and muscles get weak fast. To stay strong, astronauts work out about 2 hours a day. That includes running on a treadmill using bungee cords to act like body weight, lifting weights, and cycling. There's even a space gym. It's small, a little loud, and looks more like an old torture machine than a gym. But it helps keep them fit and grounded. Well, not really, but you get the idea. After work, astronauts can relax. They might watch a movie, call their families, read a book, or look out the window. The best one is called the cupola. The cupola is a dome with 7 windows that gives amazing views of Earth. You can see a sunrise and a sunset every 45 minutes. You can watch lightning storms from above, cities glowing at night, and the thin blue line of Earth's atmosphere, so fragile, so beautiful. Even the most experienced astronauts stop to stare. Many say it's the calmest spot on the station. Like a little sacred space. A reminder of why they're up there at all. But space life isn't all peaceful. It's cramped. It's noisy. Fans, pumps, beeping, all the time. There's no privacy. You share a bathroom with 5 people. You bump into each other a lot. And the food? Let's just say you're not going to space for a fancy meal. Still, most astronauts say the trip changes them. Not just because of the view or the science, but because of what space teaches them about Earth. Things like water, privacy, gravity, and fresh air, stuff we barely notice, become treasures in space. Every drop of water matters. Every breath is thanks to careful design. And when you see Earth, a tiny, glowing dot in a big, black sky, it changes something inside you. Living without gravity isn't just hard on the body, it changes how you see everything. It teaches you how to adapt, how to stay humble. Floating, it turns out, teaches us a lot about being human. In our next part, we'll talk about what space really does to the human body. Not just the puffiness or taller spines, but the deeper stuff. How gravity shaped our bodies over time, and what happens when we live without it for too long. So take a deep breath. Let your body relax. You're still on Earth. But just for a moment, imagine the quiet hum of a floating lab, the Earth turning slowly below, and the quiet wonder of living in orbit. So far, space sounds kinda dreamy, doesn't it? No gravity. No rush. You float from one task to the next like a ballerina underwater. The Earth glows beneath you like a nightlight for the stars. And your hair? Always full and floating perfectly. But for all its magic, space has a hidden cost. Tonight, we're going to explore what microgravity really does to your body, the strange changes, the tough surprises, and how gravity has quietly shaped us all along. Because here's the truth, your body loves gravity. It's used to it. It's been working with it since the moment you were born. Gravity tells your muscles when to work, your bones how to grow, and your blood where to flow. Take gravity away, and your body starts asking, "Wait, what's going on?" Let's begin with something small, fluid shift. On Earth, gravity pulls your body's fluids, blood, water, lymph, downward. That's why your feet swell when you stand too long, and why your head feels clear when you lie down. In space, there is no down. So, the fluids float up. Your face gets puffy. Your legs look thin. Astronauts call it the Charlie Brown effect. A big round head with little legs. Your sinuses fill up. Your voice can sound different. It's like your body is wearing an invisible suit, inside out. This fluid shift affects the eyes too. There's something called SANS, spaceflight-associated neuroocular syndrome. It causes pressure behind the eyes, flattens the eyeballs a little, and can make it harder to see. Some astronauts come back with vision that never fully returns to normal. Not ideal when your job is reading checklists, and avoiding walls. Now let's talk about bones and muscles. Even standing still on Earth works your body. Your legs hold your weight. Your back keeps you upright. Your bones stay strong because they feel pressure. In space? No weight. No pressure. So bones start to weaken. Astronauts lose about 1 to 2% of their bone strength every month in space. That's like aging 10 years in just a few months. The hips and lower back get hit the hardest. Calcium leaks out of bones, and it doesn't always come back. Muscles shrink too, especially your big ones like the thighs, calves, and back. That's why astronauts work out so much. 2 hours a day, 6 days a week. It's not about looking good, it's about survival. Without that exercise, coming back to Earth would feel like trying to run a marathon after being in bed for a month. Even your heart takes a break. In space, it doesn't have to pump blood upward, so the workload drops. The heart can shrink a bit. When astronauts return, they can feel faint or dizzy. Their heart has forgotten how to fight gravity. The balance system in your inner ear, the vestibular system, gets confused too. It needs gravity to tell which way is up. In space, it basically gives up. That's one reason astronauts feel motion sickness during the first days. Headaches, dizziness, nausea. Not exactly the heroic space life you see in movies. Now the spine. Without gravity squeezing it, your back stretches out. The bones in your spine move apart a little, so astronauts can grow up to 2 inches taller in space. Sounds cool, until you're stuck in a sleeping bag meant for someone shorter. Not so majestic now. But not all the changes are bad. Living in space has helped us learn how gravity shapes our bodies. It's taught us that bones don't just exist, they respond. Muscles don't just grow, they adapt. Even our cells act differently in space. Gene activity changes. The immune system behaves differently. Wounds heal in new ways. Space is like a big science lab. And it's not just helping astronauts. What we learn up there helps people on Earth too. Space research helps doctors understand things like bone loss, weak muscles, and how fluids move in the body. Medicine made for space is helping medicine on Earth, one floating test subject at a time. But we can't forget the mental side of space life. Living far from your family, in a small space, with a tight ski doula and only 6 other people, and nowhere to go, can be really tough. Astronauts have to deal with more than just floating around. Their bodies get confused by the lack of day and night. Their feelings can get heavy when they look down and see all of Earth below. To cope, they stay close to loved ones, follow daily routines, and find purpose in their work. They take photos, read books, play music, and yes, watch movies. Popcorn isn't allowed, sadly, but they still find digital comfort. The longer we live in space, the more we realize how deeply connected we are to gravity. It's part of us. Without it, our bodies slowly start to fall apart, quietly, gently, and in ways we don't expect. But we also learn how strong and smart we are, able to adjust and survive in such an unnatural place. Floating in space is strange, but it proves just how amazing the human body really is. In the next part of our journey, we'll shift from the body to the machines. Because to live in space, muscles aren't enough, we also need technology. From toilets to airlocks, space suits to solar panels, we'll explore the clever designs that make life in orbit possible, and how gravity, even when it's missing, still influences every detail. But first, take a deep breath. Feel the weight of your bed, your blanket, the air around you. That's gravity. It's telling you, you're home. Let's now appreciate something that doesn't usually get much attention in bedtime stories: space engineering. It's not shiny or floating. There are no silver wings or warp drives. But without it, astronauts would freeze, starve, or drift off into the void. And behind all this quiet, life-saving design is a force we barely notice: gravity. Tonight, we'll explore how gravity, even though space seems to lack it, still shapes how we build things for space. From spaceships to astronaut gear, from air systems to space toilets, gravity is the invisible engineer guiding every step. Let's start with the basics. Launching. To reach space, you must first break free from Earth's pull, and that takes a huge amount of energy. Earth's gravity is no joke. To escape it, a rocket must reach speeds over 11 kilometers per second. That's about 33 times faster than sound. That's why rockets are basically giant explosions with pointy tops. And most of what you see in a rocket isn't cargo or people, it's fuel. Huge tanks of it, built to fight the strongest force we know, gravity. But once you're in orbit, gravity doesn't disappear. It just plays a different role. Now your spaceship must work with gravity, staying balanced between falling and flying, keeping the right speed and altitude, avoiding falling back or floating away. Even the shape of a spaceship is designed with gravity in mind. Capsules like the ones from Apollo or SpaceX look blunt on purpose. That shape helps them survive the fall back to Earth, using the atmosphere and gravity to slow down and spread out heat. Now let's go inside the spaceship, where things get delicate. In zero gravity, every tiny action matters. There's no friction to stop anything. Twist a knob too hard, and it might float off. Open a bag too fast, and things will fly everywhere like glitter at a kid's party. So engineers design tools and equipment carefully. Velcro is on everything. Storage uses bungee cords. Astronauts use foot loops and handrails to hold themselves still. Labels are color-coded and feel different to the touch, because in space, there's no real up or down. Even drinking water is tricky. You can't pour it or use a regular cup. Instead, you sip from special sealed pouches using straws with clamps. It's like a high-tech juice box made by NASA, and it works. Now think about air. On Earth, we don't notice air much, it just moves. Warm air rises, cool air sinks. But in space, air just sits there. It doesn't flow. So engineers built systems with fans and vents to keep oxygen moving, carbon dioxide out, and yes, keep smells under control. Space has a smell, but we'll talk about that later. More impressive is the life support system. It keeps the air breathable, the temperature right, and the humidity safe. It filters out gases and bacteria too. It's like living in a high-tech fish tank, if the fish had laptops and exercise machines. Speaking of exercise, astronauts still need to work out. On Earth, gravity makes a treadmill work. In space, not so much. Astronauts use bungee harnesses to stay on the treadmill. Resistance machines use vacuum systems or spinning flywheels to copy gravity's effect. Without these, their muscles and bones would get dangerously weak. Now, let's talk about the part you've been curious about, toilets. In space, regular plumbing won't work. Everything floats, including waste. So toilets use gentle suction to pull waste away. Astronauts must aim carefully, strap in tight, and follow detailed instructions. Urine is cleaned and reused as drinking water. It sounds gross, but it's actually safe. NASA even jokes. Yesterday's coffee is tomorrow's coffee. Waste that can't be reused gets sealed and stored until it's burned up during re-entry. Yes, some things literally burn in the sky, which is weirdly beautiful. Even the space suit, that puffy white outfit, is a gravity design miracle. On Earth, it weighs about 300 pounds. In space, it weighs nothing, but it still has mass. Push off too hard, and you'll go spinning. Every part of the suit is carefully made to protect the astronaut while letting them move, grip tools, breathe, and stay safe. And if they do float away? There's a backup, a small jetpack called Safer. It uses little bursts of gas to bring them gently back, like finding your way home after wandering off at a party. So even though space has no gravity, everything we do up there is influenced by it. We launch to escape it. We build machines to replace it. We still feel its presence everywhere. And when astronauts come back to Earth, gravity hits them hard. Some collapse under their own weight. Others feel faint as their hearts relearn how to pump blood against pressure. One astronaut said the world felt 10 times heavier. Another said the weirdest part was needing to hold their arms up again, because they forgot what it was like to have weight. Gravity never really goes away. It's just quiet, always shaping every move, every breath, like a silent engineer watching from the shadows. In our next chapter, we'll zoom way out. We'll explore the universe itself, from stars being born to galaxies taking shape. Because gravity doesn't just pull. It creates. It sculpts. It builds everything. Let your mind drift beyond Earth, beyond the space station, beyond the solar system. Because gravity's reach is endless, and so is its story. We've already seen how gravity shapes our bodies and machines. But that's just local stuff, human scale, Earth scale. To really understand gravity, we need to go bigger. Way out in deep space, gravity is the artist behind everything. It pulls together dust clouds to make stars. It gathers stars to make galaxies. It choreographs the movement of everything we see in the sky. Let's begin small, at least in cosmic terms, with a nebula. A nebula is a big cloud of gas and dust floating in space. On its own, it just drifts peacefully. But then gravity steps in. Slowly, it pulls the particles closer. A few clump together, then more join in. As the mass grows, the pull gets stronger. Eventually, the pressure at the center gets high enough to trigger nuclear fusion. A star is born. All because gravity gently squeezed hydrogen atoms until they lit up. That's how our sun was made. And every star you see in the night sky started the same way, from a cloud of dust and gas pulled together by gravity's quiet power. Not with a bang, but with a slow, steady tightening, like the universe breathing in. Now imagine these stars don't float alone. They form in groups, clusters, held together by their shared gravity. Over time, these clusters pull more stars in. They start orbiting each other. Eventually, they become something much bigger, a galaxy. And our galaxy, the Milky Way, is one of gravity's most stunning creations. The Milky Way galaxy, our cosmic home, is made up of somewhere between 100 and 400 billion stars. These stars aren't scattered randomly. They live in spiral arms, winding bands made of gas, dust, and clouds where new stars are born. These arms twist around a bright center, all held together by gravity. It's like a celestial dance, where stars whirl around a ballroom at mind-blowing speeds. But here's the strange part. With how fast they move, the stars should fly apart. Yet they don't. Why? Because gravity holds them in place. Each star is tugged down not just by the others around it, but by a huge amount of invisible mass at the center of the galaxy. That mass includes stars and dust, but also something we can't see, dark matter. We don't know exactly what dark matter is. We can't see it or touch it, but we know it's there, because galaxies rotate way too fast for the amount of visible matter inside them. Without some kind of extra gravity, they'd fall apart like leaves blown by the wind. Whatever dark matter may be, it adds that missing gravity, the glue that holds galaxies together. And the Milky Way? It's just one galaxy among hundreds of billions. Across the universe, galaxies are scattered like bright islands in a dark ocean. They group together in clusters, then form superclusters. These structures stretch out in threads and knots across space, creating something breathtaking, the cosmic web. This cosmic web looks like glowing filaments connecting huge galaxy clusters. It's not a mess, it has shape and pattern. That's because, over billions of years, gravity has sculpted it, pulling mass into patterns as old as the universe itself. But gravity does more than just hold things together. It also bends and warps them. One of the wildest things Einstein's theory of general relativity tells us is that mass doesn't just attract, it bends space and time around it. This bending even causes light to curve, in a process called gravitational lensing. Imagine a distant galaxy sitting behind a massive cluster. As light from that galaxy travels toward us, it curves because the space around the cluster is warped. So we don't see that galaxy directly. We see a stretched or magnified version, sometimes even multiple copies. We've used this strange trick to see galaxies that are otherwise too faint to spot, and to map dark matter, which reveals itself only by how it bends the light around it. In this way, gravity becomes not just a cosmic sculptor, but a cosmic telescope. And then, we reach the extremes of gravity, black holes. Black holes form when very massive stars collapse under their own gravity. They become so dense, not even light can escape. But they're not space vacuum cleaners sucking up everything nearby. Instead, their gravity reaches far beyond them, warping space, twisting time, and causing explosions of energy that can be seen across the universe. Sometimes, entire stars get shredded if they wander too close. Yet these terrifying monsters are actually central to galaxies. In fact, nearly every galaxy, including ours, has a supermassive black hole at its center, with a mass millions or even billions of times that of our Sun. We don't fully know how these giant black holes formed, but we do know that their gravity helps keep their galaxies together. Without them, the graceful spiral shapes of galaxies might not exist. So from swirling dust to new stars, from galaxies to the great web of the cosmos, gravity is behind it all. But it works slowly. It doesn't rush. It takes billions of years to shape a galaxy. Billions more to guide the stars. Even longer to build the cosmic web that fills the universe. Gravity doesn't shout. It whispers, it waits, and it shapes. And still, we don't fully understand it. We can describe gravity, we can measure and predict what it do. Yes. But if you ask a physicist what gravity truly is, they might just shrug, and then give you a long lecture. Some scientists think gravity might not be a basic force at all. It might come from something deeper, something hidden in the quantum world that we haven't figured out yet. We'll explore that mystery soon. But for now, just remember this. When you look up at the stars, you're seeing gravity at work. Every shining point was created by gravity, held in place by it, and even the light reaching your eyes was bent and guided by gravity on its long journey. Up to this point, we've talked about gravity like it's a force, pulling on things, apples, astronauts, planets. That's how Isaac Newton saw it. But then Albert Einstein came along and changed everything. In 1915, with a sparkle in his eye and famously wild hair, Einstein introduced the theory of general relativity. It didn't just change how we see gravity, it changed how we think about space and time themselves. Let's try a simple metaphor. Think of the universe as a giant, stretchy sheet, like a bed sheet. Place a heavy bowling ball in the center. The sheet dips under the weight. Now roll a marble across the sheet. It curves toward the dip, not because the bowling ball pulls it, but because the sheet is curved. This is the key idea behind Einstein's gravity. Big objects like planets, stars, and black holes bend the fabric of space and time. Smaller objects then move through that curved space, following its shape. What we feel as gravity is really just us following the natural curves of space. So when you drop to the ground, it's not that you're being pulled, you're just following the curved path created by Earth and the fabric of space. Newton said gravity was a force acting across space. Einstein said gravity is geometry. So planets don't orbit because the sun pulls them. They ride along curved paths in space and time, like a skateboarder looping through a giant invisible bowl. And yes, it's not just space. It's space and time together, a fabric called spacetime. And spacetime can bend. That means in places where gravity is stronger, time actually moves more slowly. This isn't just theory, it's real and has been measured. Your GPS wouldn't work without it. Satellites in orbit experience slightly less gravity than we do on Earth, so their clocks run a tiny bit faster. Without corrections, your map could drift kilometers every day. Time, it turns out, is flexible. Stand on a mountain, and your head ages faster than your feet, only by a tiny bit, but it's measurable. Now imagine getting close to a black hole. These objects warp spacetime so much that time itself slows down. To someone far away, you'd appear to move in slow motion. Near the edge, called the event horizon, you could experience just minutes, while years pass for someone watching from a distance. This strange effect is called gravitational time dilation. It's one of the most poetic and eerie results of Einstein's theory. It has also been used in movies like Interstellar, where 1 hour near a black hole equals 7 years elsewhere. And as strange as that sounds, the math works. Einstein's equations have been tested again and again. Light really does bend. Clocks really do tick differently. Space missions like Gravity Probe B have even measured how Earth's gravity twists spacetime. And when gravitational waves, ripples in spacetime, were first detected in 2015, 100 years after Einstein predicted them, it confirmed yet another part of his theory. These waves come from events like black holes crashing into each other, and they stretch and squeeze space as they pass, though only by an amount thousands of times smaller than an atom. Even so, with tools like LIGO, scientists have heard the universe hum for the first time. Einstein's theory doesn't just explain how things move. It opens a window into the hearts of stars, the edges of black holes, and the earliest moments of the universe. But it's not perfect. As powerful as general relativity is, it breaks down when we look at tiny things, atoms, particles, the quantum world. There, we use a different theory, quantum mechanics. But quantum mechanics and general relativity don't get along. So scientists have been on a long quest to bring them together, to find a unified theory of gravity that works at both huge and tiny scales. We have ideas, string theory, loop quantum gravity, and others. But so far, no final answer. It's like having two perfect maps, one for cities, one for forests, but not knowing how to draw the trail that links them. Even so, general relativity is one of the most beautiful and accurate ideas in science. It showed us that gravity isn't a force, it's geometry. And that idea completely changed how we understand the universe. It's not easy to picture. Sometimes, it feels downright strange. But the universe doesn't promise to make sense to us. It only promises to be real. And sometimes, reality is stranger than we ever imagined. Take a moment and think about it. Right now, as you sit wherever you are, your body is resting on a planet that's bending space and time. Your weight is not from a force pulling you down, it's because you're riding a curved path in spacetime that leads to the floor. Each star above you is shaping spacetime around it. Light from distant galaxies reaches your eyes only after being twisted by invisible curves in the cosmos. Even time itself flows differently depending on where you are. The universe isn't still, it's alive with motion. A rippling fabric. A web of curves and dips. All shaped by the geometry of reality. Einstein once said, "Reality is merely an illusion, albeit a very persistent one." And maybe gravity is the most persistent illusion of them all. It's not really a pull, it's more like a path. And we're almost at the edge now. In the next chapter, we'll quietly step past science and into philosophy. We'll ask if gravity is truly a basic part of nature, or if it's something even stranger. Could it be something that only shows up when we try to measure it? That's a deeper mystery. But for now, let's pause. Let's rest in this gentle idea. The universe isn't solid or unchanging. It bends slightly. And we, like marbles on a soft blanket, are just rolling along curves made by something much bigger than us. We've followed gravity from falling apples to spinning galaxies, from the heavy feeling in your chest to the shape of space itself. We've trusted it, leaned on it, even imagined it as geometry, thanks to Einstein. But what if gravity isn't real? Not real in the way we usually think. What if gravity, the steady force we've built our universe around, isn't a basic force at all? What if it's more like a trick? A side effect of something even deeper? That's the question some scientists and philosophers have been quietly asking for years. And tonight, we'll gently explore that strange place between solid science and gentle guessing, where the rules aren't fully clear, and gravity might be something even more mysterious than we thought. Let's begin with the word emergence. In science, something is emergent if it appears when smaller parts work together, even if those parts don't have that thing on their own. Think about temperature. One molecule doesn't have a temperature. But when trillions of molecules move wildly together, we call that motion heat. So, heat isn't a basic thing, it's a kind of pattern. An emergent property. Now think about gravity. What if gravity is like temperature? Not a force, or a curve in space, but something that comes from something deeper? This is the heart of a bold idea in physics, entropic gravity. It was introduced by scientist Erik Verlinde in 2011. He suggested that gravity doesn't come from a pull or from curved space, but from the way the universe tries to increase entropy, or disorder. In other words, gravity might be the result of the universe constantly moving toward the most likely state, full of disorder and scattered information. Imagine marbles rolling to the bottom of a bowl. They don't go there because something pulls them, they go there because it's the most stable, likely place. Gravity, in this view, is like that, things moving toward where the information wants them to be. If this sounds confusing, you're not alone. It is. You wouldn't feel this lying in bed or see it by tossing a ball. But this idea might help explain some big mysteries in science, like dark matter. We can only see a tiny bit of the matter in the universe. Galaxies spin faster than they should, based on the stars we see. So, we think something invisible must be adding gravity, something we call dark matter. But after decades of searching, we still haven't found it. Verlinde's idea says maybe we don't need to. If gravity is an emergent thing, maybe we're just using the wrong math. Maybe at big cosmic scales, space behaves differently when entropy takes over. No dark particles, no mystery stuff, just a new way of thinking. Of course, entropic gravity is not proven. Many scientists don't accept it yet. It hasn't replaced Einstein's theory or Newton's. But it offers a glimpse, a possible clue, that gravity might not be what we thought. And it's not the only strange idea. Some scientists believe in something even more mind-bending, the holographic principle. This idea says that our entire 3D universe might actually be a projection. Like a 3D image coming from a 2D surface, like a cosmic hologram. This isn't science fiction. It comes from real research into black holes. When scientists studied black holes, they found something odd. The amount of information a black hole can hold isn't based on its volume, but on its surface area. It's like everything that falls into a black hole is written on its outer edge, not stored inside. That strange idea led scientists like Gerard T. Hooft and Leonard Susskind to ask, what if the whole universe works that way? If that's true, gravity might just be a side effect of this giant projection. Not a force, not a curve, just a trick. An illusion created by deeper rules about information. It's important to pause here. These aren't facts. They're ideas. Guesses backed by real math, real studies, and the farthest edge of what science can see right now. But they ask big questions, not just about gravity, but about reality itself. Think about it. For centuries we thought Earth was flat, because it felt flat. Then we learned it was round. Then we learned it spins. Then we found out it orbits the sun. Then we learned the sun moves too. Every step changed not just our science, but our view of ourselves. We're not the center. We're not standing still. We're not even fixed in place. And now, some scientists are asking, what if even gravity, the force we thought we understood best, is just one more layer? One more illusion in a deeper reality? It's like waking up in a house you've lived in your whole life, and realizing the walls are just projections. The floor is a pattern. The furniture is a trick. And yet, the house still works. You don't fall through the floor. Gravity still holds you. The illusion is real enough to live in. GPS still works. Planets still orbit. Apples still fall. Newton and Einstein were right, for their parts of the story. But beyond that, something more might be waiting. So what does this mean for you, lying there trying to sleep? It means the universe might be even deeper, stranger, and more beautiful than we ever imagined. That the weight you feel might be entropy's soft push. That your feet stay on the ground because information prefers it that way. It means science is not finished. It's never finished. Each answer brings more questions. Each theory lights up a hallway with more doors. And gravity? Maybe it's more than just a force. Maybe it's an invitation. A whisper saying, look closer. I might be something else. In the final chapter, we'll come home. Not in space, not near black holes, but back on Earth. We'll reflect on what gravity means, not just for the universe but for us. How something so quiet and invisible can still hold everything together.